So welcome to the last part of Lecture 7 for Math 2R03. In this part here, I just kind of want to show you some consequence of this idea of taking a linearly independent set and expanding it to a basis. So here we have a theorem which says that we have a vector space of a finite dimensional and use a subspace of it. Then what we can actually show is that there's another space W such that V can be written as a direct sum of U and W. So what we need to do is first find a subspace W and then show that its V can be written as a direct sum of these two things. So what we're going to see here is you're going to use some of the results of the previous lecture here, our previous part, to expand a linearly independent set of elements to a basis. So U is finite dimensional, so it has a basis, U1 through UP, right? So those vectors all live inside of U, but they also live inside of V. So as a consequence, these vectors are also linearly independent in V. Okay, so they are linearly independent in U. They continue to be linearly independent in V. So by the previous result, what we can do is we can extend this list to a basis of V, right? So the way you want to think about this is we have U1 through UP, and now I'm going to add a bunch of new vectors. I'm not sure how many I'll have to add, but I'll have to add some vectors such that this part here is a basis for U. And if I take all the vectors from U1 to WT, this is a basis for the vector space V. And what we're going to do is now we're going to let W, okay, let W be the space spanned by W1 through WT. Now, clearly W is a subspace of V. So we have actually kind of satisfied this condition right here. So we have a subspace of V, and the claim is that this is actually the subspace that we need, that this will be satisfied. Now, I'm not going to work out all the details because they are given in the textbook, and I'll just point out what you need to check. Okay, so to check, two things. First of all is that V is the sum of these two vector spaces. And that's actually not too hard. You can kind of see it right here. If you take any element in V, it can be written as a linear combination of these guys because it's a basis. Here, I'll put my hand here. It can be written as a linear combination of these guys. And then if you just look at the things that are a linear combination of the U's, that lives in U, and you look at the things that are a linear combination of the W's, it lives inside a W. So this part is actually very straightforward to check. And then the second part that you would need to check is that the intersection of these two subspaces is 0. And if you can prove these two facts, you actually would then get that V is a direct sum of these two things. And let me just mention here that if you want to see the details, you can see the details in the textbook. Okay, but you might want to try to see if you can prove those details by yourself. Get used to proving things like this sort of thing. So instead, let me just spend some time on an example. Okay, so let's say we take U is equal to the span of 1, 2. And if you want to kind of visualize what that is, right, you're taking a vector, this is the vector here, and this would be 1, and this would be 2. And the span would be all the things on this dotted line, right? So this green thing here is the span of 1, 1, 2. And from the last example, right, we proved that r squared is equal to the span of the vector 1, 2 and 1, 0. Hopefully that's the right order. Let me just double check, make sure that was what I proved here. Yep, 1, 0, just double checking. Okay, looks good. So a span of these guys. And now what we do is we let W equal to the span of 1, 0. So what we have is R2 is equal to U direct sum W. Okay, and we can draw a little bit of a picture here of what's going on. Let's look at my axes again. And I have my space U here. This is U. And then W is going to be the span of 1, 0. So there's 1, 0. So the red line is W. So everything in R2 can be written as something in here plus something in here. Okay, so that's what the previous result tells us. Okay, so let me just put this here, bring myself back up. So today, kind of the main ideas is what is a basis? So a basis combines the notion of a spanning set and a linearly independent set. And some ways the two most important results in today's lecture that get used kind of almost all the time is that you can shrink spanning sets to bases or you can expand a linear independent set to a basis. And these are very useful results when you're doing proofs. You can just say that I can do this. I have a spanning set and I can make a basis. I have a linear independent set, I can expand it to make a basis. So that's it for today's lecture on bases. I will see you in lecture 8. Have a great day.